Great. Okay.
You record it to the cloud?
Yeah.
Hello, we are Panama Possibilities, and we'll be talking about the water distribution system we designed for the Macambo Araba community.
I'm Caitlin Birch. I'm a civil engineering student and I worked on the shade covered designs.
I'm Maddie Holman. I'm a mechanical engineering student, and I worked on the hydraulics of the system.
I'm Louis Seckla. I'm a mechanical engineer and I work on the network layout.
I'm Carly Leonard. I am an environmental engineer and I currently work on the site network.
Our sponsors for the project were Dr. David Watkins and Dr. Melanie Cooper Watkins, and our sponsor was Rick Montanari with Footprint Possibilities.
So just for a brief overview of what we're going to go through today is we'll start with project background, talk about our proposed design, and then move into the cost estimate and construction schedule, and then finish up with some project impacts and final recommendations.
So here is a picture of where Macambo is located in Panama. It's north of Panama City, near the Panama Canal, and the population of the community is about 30. So currently the community has no access to clean drinking water. So all their water comes from either bottled truck deliveries or deliveries from big water tank trucks, or just collecting it from the rain. But recently the community of Chilibre has extended their pipe network to be close enough to the community for them to feel what's happening to it. So the community of Macambo is located in a very mountainous area. The top or the local high point of the area is 435 meters and the low point is 60, which makes about 300-meter elevation change over the place. You can see the top topographic map of the area and also a sector breakdown of the area based on the geographic locations of the different sectors. Here's the population breakdown of the different sectors. You can see sectors 1 and 2 are by far more populated than the rest of the community. Sector 2 also has a lot of the amenities of the community, such as a clinic, church, and school with both 75 students. The picture is a picture of the nearby Kunanega community, which is about a mile south of Macambo. It's an area where our sponsor has worked with in the past.
So we had a few goals that we wanted to achieve with this project. First off, we wanted to provide every house with clean drinking water, and if we could, adequate pressure to run all of their utilities within the home. We wanted to do this and supply them with 50 liters of water per day per person, as well as providing a 1-day storage capacity so that in case of emergency, they still have water for at least a day. In order to do this, we had a few requirements that we had to take into consideration. And so first we wanted to include the pipeline into the municipal IDOC tie-in, like Louis was talking about before, from Chilibre. And then we also wanted to make minimal maintenance for the system. So we really minimized our mechanical parts and tried to make it a gravity-fed system with no pumps. We also had some limited materials, so we have to take that into consideration as well. For the project, we have some governing bodies that we have to account for, and these include the Panamanian government, IDOM, which is the water authority, and then the Ministry of Health. So the Panamanian government requires that all of the water storage be in a secured location. So that's why we provide a fence around our water storage, which Caitlin will talk about in a little bit. And then I also want to point out that our system is meant to be temporary, designed for 10 to 15 years. It is not built to IDOC standards or US standards, but we're still making sure that we're maintaining a high level of water quality and maintaining human health.
So here's a picture of the network layout for the pipe system. As I said before, the municipal line connection is inside of the community, which is directly connected to tank farm 1, which is just a basic roofing of tanks. From there, the pipelines goes around the ridge line and begins to enter the community, separates at bifurcation ring 1, which kind of separates the sector 1 deviation from the sectors 2, 3, and 4. You can see in the top right, in the legend, housing connections are denoted by the plus marks, and there's other service points that are sponsors previously marked out. In the top left, the table shows the different accessories for the pipe. There's different tanks, valves, and different connections for the houses and everything shown up there. And the bottom left shows the different PVC pipe lengths that are needed for the pipe system. The 4-inch pipe mostly takes place in the light blue area between the community and the municipal line. The 2-inch pipe is the branching pipe that travels through the different sectors. And then the 1/2-inch pipe is the pipe that connects the 2-inch pipe to the houses itself. All the PVC pipe is UV resistant to avoid breakdown from the bright sun.
These are the storage tanks used to control the pressure and flow of the system. They're made of black polyethylene. We used 8,000 and 6,000 liter tanks due to availability from the supplier Bombasa. So there's 2 main tank farms which will hold 10 of the 8,000 liter tanks, and then the first tank farm can expand to another 6 tanks as the community grows. And then there will be 3 6,000 liter tanks. One will be a pressure brake tank in sector 1 due to high pressures. One will be a tank for the school, and then one will be a holding tank in sector 4 because they do not receive enough water, and so that'll hold water for the hours that they don't have sufficient pressure.
So with the tanks that we'll be providing, we need to have shade covers. Since there's a lot of sun in Panama, the dechlorination could occur and making the water non-potable. So these shade covers help provide protection from the sun and other branches or tree limbs potentially from falling onto it. So the materials that we used for these shade covers were 14 gauge C-channel pressed metal studs with a corrugated metal roof on top of it. Then these are going to be encased in concrete on the bottom, or concrete pillars on the bottom, and then have a gravel base for the tanks to lay on or to sit on. Fencing around the perimeter will occur about 1 meter offside from all the sides of the tanks. This protects it from people potentially getting into the farms and tampering with the water supply. So overall, we have 2 large tank shade covers. One is 40 foot by 24 feet, and this one holds the 10 of the 8,000 liter tanks. And then, like Maddie said, we have the 3 small single shade covers, which are each 8 by 8, and will hold the 1 6,000 liter tank. We were unable to find a dimension for the 6,000 liter tank, but we assumed it was proportionately smaller, so this will hold it inside there. So here you can see an example of an overview for the large tank structure. So there will be some central posts to help keep the rafters going across from sagging. And you can also see some shear bracing along the sides and on the front of it. So here is an example of how the tanks will be sitting inside of the large structure. So here you can see 4 of the tanks with a central aisleway, and this will give you access to 2 tanks that are sitting on the inside of the structure. And then you can see an up close look at the shear bracing and how the joists are inset on the posts there. You can also see how it slopes from 15 feet in the front down to 14 feet in the back, allowing for adequate runoff off the roof. Here's an overlook of how the tanks could potentially sit inside of the structure. So we have the 5 and 5 with the aisleway going in, and then they can also have it a looking glass to see how much water is in the tanks, as these are black tanks and not being able to be seen through. So here's a look at the small shade structure. We have the bracing and shear bracing to allow for no wrapping of the structure. And then how the overview of the roof will lay out along with the cross bracing there. There is a 20-inch overhang on both of these structures to allow for coverage throughout the day and the sunlight. And these these shade covers will be oriented with the arc of the sun to allow for the longest amount of shade possible throughout the day. So our sponsor gave us examples of different type of corrugated metal roofing that was used in the past. And they like to use the undulato type of corrugated metal roof. So we are suggesting to be using that as well here. And this will be overlapped as the pieces need to be put in place with self-tapping screws. So unlike in the US where we would typically use structural steel, here we'll be taking 2 C-channel pieces of pressed metal studs, putting them back to back and then bolting together with 5 bolts every 24 inches down the post. This will then be encased in concrete pillars 12 inches down and 18 inches total in depth for them.
So another important detail of the pipe network is the pipe suspension bridges. And for areas between the municipal line connection and the community, it tends to be very steep and difficult terrain, so it'd be necessary for us to span that distance with these bridges. You can see a picture of the bridge already in use today. The materials for the bridge are the PVC water pipeline, the steel cable and cable clamps, the cut PVC support ring, and the concrete block and the anchor. So here's a detail of the pipe suspension bridges for 4-inch sections. On the top left is the block and anchor eye-hole design. This is for instances where there's no tree close enough to connect. On the right shows the tree connection design. This is for, you can see as in the picture that the cable wraps around the tree and then holds up the cuts PVC support rings and which hold up the pipeline. Our sponsors set a maximum gap distance of 15 meters to prevent excessive sag. The maximum amount of sag would be about 2.2 meters for the 4-inch pipeline. So for our project, we assume that there'd be about a bridge needed for every 150 meters. They'd average about 30 meters in length. This would mean that we need about 10 total bridges necessary. And on the Google Earth profile, you can see a few of the potential locations that would need a bridge.
So the pipe will be excavated about 1 meter deep along the entire way of the path. However, in areas where there might be a lot of rock or they're unable to get in excavation equipment, the pipe will need to be laid on the ground. So to prevent people from potentially getting access to the pipe or animals getting into the pipe, we're suggesting using a concrete covered pipe. So the pipe will be laid on the ground with number 3 rebar laying parallel on both sides of the length of the pipe. Then number 3 rebar stirrups will be bent over the pipe to help keep it in place. The stirrups will be placed every 24 inches across the length of the concrete covered pipe. 2,500 PSI concrete will be then laid over the top of the length of the pipe in a 3-inch thick layer to keep it protected.
So using all this information about our design, we put the network into the EPA net simulation so that we could look at any possible design issues, areas that we may need to address. So what we found from the simulation is that there were some high pressures at low elevations at the end of some of the branches. And then specifically in sector 4, the end of that branch to the north end of the community is at a high elevation. So for all parts of the day, that area, those houses were not getting adequate pressure to their houses. We're also experiencing some siphoning between bifurcation ring 1 and tank farm 2 due to the uneven terrain. So we needed to address all of those issues. And we did this by adding some pressure brake tanks and then putting in pressure reducing valve. And then also we are accounting for some air admittance and air release valves to add to the siphoning areas, and then adding an extra storage tank to the areas where they're not getting adequate pressure so that they can still have water access throughout the whole day. These are some examples of the simulation. Each of the circle represents a demand node and measures the pressure at that point. Some of them are clusters of houses, some of them are just intermittent points along the pipeline. You can see in the 8 o'clock hour that it's pretty good. There's no high pressures. High pressure would be indicated by a red circle, and extremely low pressures, negative pressures are shown in dark blue. So you can see at the very top of sector 4, that's where those negative pressures are occurring, and that's why we added that storage tank there. In the 6 o'clock hour, you can see that there's still some siphoning occurring on that branch between bifurcation ring 1 and tank farm 2. It's those dark blue dots in the middle there. And that's where we'll be adding air admittance and air release valves at local high and low points. We also have the pressure brake tank along to the south. And that was because those pressures were too high farther down that branch. And so that fixed that issue, as well as pressure release valve in sector 2 that reduced the pressures in sector 2 and 4.
So for this model, we projected a water usage over 24 hours. This was for one household of 4 people. We designed a system based off of similar models in South American countries with peaks at 8 a.m. and 6 p.m. This correlates with the workday, along with when people will be doing a majority of the washing and cleaning at the house. We also recognize that the water usage will change from what they're currently using to when they have running water. So this is projecting what their water usage will be when they have running water.
So for our cost estimate, we used RS means to get labor rates for the project, for the entire length of the project, along with looking up different materials that will be used on it. So as you can see here, the final cost came out to be $604,000, which includes a 3% increase for inflation, as this will be occurring in 2022. The highest cost is the shade covers at $204,000. We used steel C-channel beams or bars instead of the pressed metal studs as our sponsor will be using. And the total cost for that came out to be around $55,000 for that. With there being about 12 to 13 miles of total running pipe throughout the project, the running pipe was also a high cost at $196,000. With the suspension bridges, we estimated that there will only be 10 of these bridges, but this could also change as the topography is not exactly set out for sure right now. With that, the concrete amount could also potentially change with the amount that will need to be placed above ground for it.
Next, to create a construction schedule, we designed a critical path. So this indicates all the different tasks that need to take place and how long they will take to construct. And we found that the critical path will be to run the 2-inch pipe through the populated area, and then subsequently to connect the 1/2-inch pipe that will connect to the main lines to each household. And so this is something that's going to need to start construction right away. You can see in the construction schedule then, it will take 80 days total, about 3 months, and we plan to start next spring. And the people will have running water by the end of summer. This is due to when we assume funding will be secured from the Panamanian government. The construction plan will vary based on the work crew that is available.
So along with all the other deliverables that we created, we also wrote up a sedimentation and erosion control plan, as there's a lot of excavation occurring in the area. So we don't want any sediment to be leaving the sites. So we suggested to have silt fencing around the perimeter. With the amount of concrete that's also going to be used, concrete washouts are also highly suggested so that that also does not get into potential water systems or waterways in the area. A job safety plan was also written up, suggesting the PPE that workers to be using. And since this is occurring in a currently lived in environment, public safety things that should be included as well, such as like signs and areas that are marked to be kept out of. And along with that, emergency contacts and locations of local hospitals as well. An operation and maintenance guide was also written up to include information about the installation, maintenance, and how to stop and start the water distribution system. Regulations for this system and the roles and responsibilities were also laid out in this plan.
We also want to talk about our project impacts, as it is a fairly large project. We evaluated these based on the National Environmental Policy Act checklist, or NEPA. And to do this, we mostly looked at the global social and cultural impacts. So globally, we're influencing environmental justice as we're providing drinkable water to a low-income community, and also providing them with jobs and a little bit of an economic boost. This may also impact immigration patterns to the area, people move through Panama quite often from the US and looking for jobs. So this is in close proximity to Panama City and now has electric and running water. So it may become a popular place for people to settle down. Socially, it's going to affect community cohesion. There'll be a level of organization that's required to run the water distribution system that has probably not been needed before. They'll need probably a water committee to collect dues, maintain all of the admin stuff, and then also maintenance type things. And finally, culturally, this could be impacted as people were probably moving from rural areas and have limited experience with centralized utilities. So they may not be used to that, and that might be a bit of an adjustment for them.
So some of our final recommendations for this project is to continue pursuing and getting approval from the Panamanian government and finally getting funding for this project. Using our drawings and models and taking them to professional engineers to get them finalized to be used in the system. Hiring a work crew and designing a project construction plan for this project. And then once it's all done, to maintain regular maintenance so that we can continue providing clean and safe water to the people of Macambo Arriba. Thank you. Any questions?
Why did you choose steel for the structure of the
So using timber in that area isn't a viable solution since there are a lot of termites and insects, making it, there would have to be a lot of chemicals continuously used, and that's not quite sustainable for it. Steel was the next best option, but that is really quite expensive to be using in Panama. So our sponsor gave us examples of pressed metal steel studs that were used in the past and have worked well with this type of project.
Is that part of the country have a lot of issues with a lot of rainfall where they have like mudslides? Is that something you guys consider for putting pipes on the ground?
With the pipes on the ground, yes, since in the areas that are mountainous and such like that, and then they'll be a meter deep into the ground as well for that.
So I was looking at this cover. What were the size?
Those will all be 2-inch pipes. So the 2-inch pipe will run through the communities, which is where we're projecting will not be able to dig through the rock. Places that they can't dig through the rock will most likely be the 4-inch pipe where they can do bridges.
So you're gonna custom sizes.
Correct.
Mhm.
And then it's constructed with the rebar on top and then like it's under the rebar.
So like, yeah, the rebar goes like alongside the pipe and then the strips go over that, like holding it all together. And those will be like epoxied into the ground, I believe that's what we had said.
I was really curious with the social aspect of it, like people getting used to it. Was that the guy's budget, or is there something out there already? Like in communities like this, when something like this happens, is there something out there already? Like educationally, how you would go in and educate the people on it? Seems to me like that would be a really big issue. It's getting them used to this.
Yeah, that's a really good question. Unfortunately, we weren't able to actually go to Panama this year, so we didn't get a lot of feedback from the community. But I'm sure there's a lot of interest from the Panamanian government right now, and they are hoping to eventually upgrade it to a municipal system. So I would hope that the Panamanian government would have ways to educate them and make sure. I would assume our project sponsor also is a little of this. I'm not 100% sure about that, but
We also are a manual, so it doesn't outline every aspect, but it does explain cleaning of the tanks, how to flush the system, how often you have to maintain it, and what to do in certain situations. So it's minimal.
Is the population there literate? Would they be able to read all that? Is that, you know, just curious.
I'm not sure about that.
Okay.
Just a general question. what do you think was the biggest challenge from this project, or what's something you know now that you wish you knew at the beginning of the project?
The design changed a lot through the population. We initially thought there'd be a few hundred maybe, and then we got census data that said maybe almost 1,000. And then we did some population growth models and realized it'd be about 1,500. And then last minute it changed from 3 people per household to 4, which increased the total population at the end of the time span to about 2,000 people. And then a lot of the other designs changed as well. So like the wood, Caitlin had made some really good wood drawings. Timber drawings. Sorry.
Yeah. So I had a few of the structural timber designs done for it, and then it was when we had shown that to our sponsor, we realized about the termites. So then we had to go in and create again with the steel. And then I had never heard about the C channel being just like placed back to back by that. So that was also a new kind of design detail that I hadn't heard of before.
Something in the chat.
Oh. Just stop the recording.
Your presentations that, round up this section.